Ever felt like you're just, drowning in a sea of information? All these articles, studies, reports. How do you even know what to trust?
It's overwhelming, right? And what's really important, what does it actually mean for you?
Exactly. So today we're taking a deep dive. We're going right to the foundations of how reliable knowledge gets created, how it's analyzed, how it's shared.
We're going behind the scenes, looking at research methodology, analytical data.
And those really crucial ethical guardrails that, well, make it all work.
Indeed. We're drawing from a pretty comprehensive handbook of research methodology and also an overview of qualitative research methods.
Our mission, really, is to equip you with a kind of researcher's lens.
Yeah, helping you critically evaluate all that information you bump into every single day.
So get ready, because we're about to unpack the secrets to being, genuinely well-informed. All right, let's kick things off. When we talk about research, what are we really talking about? It's definitely more than just a quick search online, right?
Oh, absolutely. At its core, research is systematic. It's a process. Creswell breaks it down nicely. You pose a question, you collect data to answer it, and then you present that answer.
Okay, straightforward enough.
And Kothari adds, it's about the manipulation of things, concepts, or symbols for the purpose of generalizing to extend, correct, or verify knowledge.
Verifying knowledge. That part really stands out to me.
It should.
Because our sources emphasize that research has to be systematic and critical. Yeah. Orderliness is the key word they use. Findings aren't just one-offs.
Exactly. They have to be verifiable. Anyone who takes the trouble should be able to follow your steps and see if they get the same results.
So what makes that possible? What are the sort of pillars of that?
Well, first, there's objectivity. The researcher has to actively resist their own bias. It's about testing hypotheses, not just, proving what you want to believe.
Letting the data lead, essentially.
Precisely. Then, precision. This comes through using statistical methods carefully, making sure conclusions mean exactly what they say. Think measures of central tendency, correlation.
We'll probably dig into those later.
We will. And finally, design. A specified step-by-step process, defining the problem, the hypothesis, how you'll collect and analyze data, test it, report it.
That whole blueprint allows for replication, for verification.
Exactly right.
Just understanding these foundations helps build trust, doesn't it? When you encounter a study, knowing these principles exist helps you gauge its reliability.
It's like checking the foundations before you trust the building.
So why does all this rigorous process matter? For you, listening right now, why should you care?
Well, research isn't just locked away in universities. It has huge real-world importance. Companies use it all the time, like with consumer satisfaction surveys to make products better.
So achieving goals.
Achieving goals, sparking new ideas, uncovering facts. It fuels deeper understanding and analytical thinking everywhere.
Yeah, it sounds crucial for navigating complexity, making better decisions. Our source says it helps disapprove of lies, uphold truth, and build knowledge that is reliable and authentic.
That's a powerful way to put it. It also helps us figure out what's not working in a project, uncovering antagonistic elements, maybe.
Right. Finding the friction points.
Yeah. And all of this builds credibility for any argument. It gives a solid base for new ideas. But, it all starts with the right question.
The research problem, an area that needs meaningful understanding.
Exactly.
Which leads to the big question. How do you even decide what to research? The sources list quite a few things to consider.
They do. Personal inclination matters, of course, but also resources, money, time. How important is the problem, relatively speaking? Your own knowledge.
Practicality, timeliness, data availability, even the area's culture. It sounds like a balancing act.
It definitely is, but there's a structured way to approach it. Start broad, say sports education. Narrow it down. Maybe focus on soccer clubs. Choose a manageable piece of that. Then formulate specific research questions. And finally, set clear objectives. Use action verbs to examine, to investigate.
So an aim might be like to examine factors contributing to muscle retention in elderly people.
Perfect. And then objectives could be things like assessing the link between sedentary habits and muscle atrophy.
It forces you to be really clear up front. Thinking about a project you might be facing, defining those objectives, that could really change your whole approach, couldn't it?
Absolutely. Clarity at the start saves a lot of trouble later.
Okay, so you've got your question. Now, how do you find out what's already known? And then, how do you gather new information?
Right. First step is usually the scientific literature. That's the main way researchers communicate results. It's the permanent record of the collective achievements of the scientific community.
So you do a literature review.
Exactly. You survey those sources, get familiar with what's known, and show you've done your homework.
Standing on the shoulders of giants, as the saying goes.
Precisely. Then comes data collection. Broadly, you've got primary data that's raw, first-hand info you collect for your specific study, like interview transcripts, survey responses you gathered yourself.
Okay, fresh data.
Right. And then secondary data, that's second-hand information. Commentary, analysis from other researchers, think journal articles, summarizing studies, academic books, reports.
Got it. And ensuring credibility is vital here, which brings us to citations.
Absolutely essential. Citations acknowledge someone else's intellectual property. You have to give credit. Anything you use, journal, book, website, even a movie, sometimes needs a citation.
And there are systems for this, right? Like indexes.
Yes. Citation indexes let researchers track the impact of an article, see who's citing it. And in scientific writing, you typically see in-text references like maybe Smith 2020, and then a full reference list at the end.
Using specific styles like APA or Vancouver.
Those are very common ones, yes.
What about something really specific, like a patent? How does that fit in?
Good question. A patent grants an exclusive right for an invention, but it also discloses technical information to the public. So patent literature is a unique kind of source, covering inventions, utility models, industrial designs.
So the next time you read a news story citing a study, it's worth thinking. Are they talking about primary data, the original source, or secondary data, someone's analysis?
And maybe wondering how thoroughly they really checked the existing literature first.
Good point. Did they build on what's known or just repeat it? Okay, let's shift gears a bit. We've talked about gathering knowledge, but sometimes research involves getting really practical, like getting your hands dirty almost.
Definitely. You might think research is all abstract, but often it's about fundamental techniques, like separating things.
Separating things.
Yeah. Think about chemistry or materials science. Matter in nature is usually a mixture, right? Not pure stuff. Air is a mix of gases. Seawater is salts and water.
And that's different from a compound, where elements are chemically bonded.
Exactly. In a mixture, the components keep their own properties. And these mixtures can be homogeneous, totally uniform, like sugar dissolved in water.
Or heterogeneous, where you can see the different parts, like oil and water.
Right. And the goal of separation techniques is critical, maybe to get a pure compound, remove impurities, or just analyze the components.
It's interesting, we can even classify mixtures by particle size. Solutions, colloids, suspensions.
Yes, based on how big the particles are, from tiny ions in solutions to larger bits in suspensions.
So how do scientists actually do the separating? Our sources list a whole bunch of methods.
Oh, yeah. For dry stuff, you've got simple things like hand-picking stones from grain, threshing, winnowing, using wind, sieving by size.
Magnetic separation, too.
Right. And for wet mixtures, techniques like evaporation, getting salt from water, filtration for solids and liquids, sedimentation, letting solids settle out.
Distillation, using boiling points.
Yep. Sublimation, where a solid goes straight to gas, like camphor. Crystallization, to form pure crystals. Using a separation funnel for liquids that don't mix, like oil and water.
Wow. And it gets even more specific with things like extraction, right?
Yeah.
Pulling active compounds from plants.
Exactly. Using solvents, with methods ranging from traditional ones like maceration or sock slit extraction to newer techniques.
You know, this whole idea of separation,
Yeah.
it feels like a powerful metaphor for what we do with information too, right?
It really is, distilling key insights, filtering out the noise from the mixture of data we face every day. It's about isolating what matters.
Getting to the core truth, the pure signal, before we act on it. So that's a deep dive into separation. But doing this kind of work, especially in labs, brings up a huge topic. Safety. Our sources are crystal clear. Safety isn't optional. It's core to the process.
Absolutely paramount. Labs, whether in schools or research centers, often use a wide range of chemicals. Acids, bases, things that are corrosive, toxic, even potentially explosive.
And regulations exist for a reason, like the Occupational Safety and Health Act, PPE gloves, coats, masks. It's all part of it.
Indeed. And it's about the details. Instruments need regular checks, proper labeling. Chemicals need careful storage and disposal. Simple rules like never add water to acid are critical.
It's about understanding the inherent risks of certain materials too, isn't it? Like those alkali metals.
Oh, yes. Group I metals, lithium, sodium, potassium, react violently with water. They produce flammable hydrogen gas. They need special storage, like under kerosene.
In group 2, alkaline earths like magnesium.
Also, water reactive. Magnesium powder is particularly nasty, burns intensely, and water can actually make it worse.
What about halogens like chlorine?
Group 7. Fluorine, chlorine, bromine. Not flammable themselves, but highly reactive and toxic. Chlorine gas forms corrosive acids if you inhale it.
Even noble gases, which we think of as safe.
Group 8. Helium, neon, argon. They are inert and non-toxic, but if they leak uncontrollably in an enclosed space, they can displace oxygen and cause asphyxiation. Plus, they're often handled as hazardous cryogenic liquids.
That raises another point, the reactions themselves. Exothermic versus endothermic.
Right. Exothermic reactions release energy, heat, light, sound. They can be dangerous, potentially explosive. Endothermic reactions absorb energy.
And materials can be sensitive to shock, friction, or even ignite spontaneously.
Yes, that's pyrophoric igniting in air below about 54 Celsius. Some form explosive peroxides over time. And cryogenic liquids, supercooled below nectar 90 Celsius, can cause severe tissue damage on contact.
Beyond the physical dangers, there are also health hazards. How chemicals enter the body matters hugely.
Absolutely. Inhalation of gases or vapors, skin and eye contact, accidental ingestion while you never eat or drink in a lab, and injection maybe from a needle stick or broken glass.
So proper ventilation, fume hoods, PPE, strict lab practices, it's all essential.
It is. This deep dive into safety really highlights the immense responsibility involved. Careful planning, meticulous handling. It's what prevents accidents.
Okay, so data's been collected, safely we hope. Now it's time to make sense of it all. Analytical data is where the rubber meets the road for decision-making.
It really is. Evaluating that data is about quality assurance, accuracy, and precision. We use statistics to figure out how confident we can be in our findings.
And here's that distinction again that always gets me thinking. Precision versus accuracy.
Right. Worth repeating. Precision is consistency hitting the same spot repeatedly.
Even if it's the wrong spot.
Exactly. Accuracy is hitting the right spot, how close you are to the true value. You ideally want both, but they are different things.
And errors are inevitable, but we need to understand them.
We do. There are determinate or systematic errors. These affect results consistently, maybe due to faulty calibration or a flawed method. They're often correctable. Then, random or indeterminate errors. These are unpredictable variations, just part of the limits of observation. You can minimize them, but not eliminate them entirely.
And gross errors.
Those are the big mistakes: spilled samples, wrong chemical, usually obvious, hopefully avoidable.
Okay, let's get into the basic tools for summarizing data. Measures of central tendency.
Yep. The mean, that's the simple arithmetic average, the median, the middle value when you line everything up in order, and the value that shows up most often.
And thinking back to that Jeff Bezos example, sometimes the median tells a more, well, representative story than the mean when there are extreme values.
Precisely. The mean can be easily skewed.
And what about how spread out the data is?
That's where measures of dispersion come in. The most common is standard deviation. It tells you on average how far each data point is from the mean.
So a small standard deviation means data points are clustered tightly.
Right. And a large one means they're more spread out. In a normal bell curve, about 68% of data falls within one standard deviation of the mean. Variance is just the square of the standard deviation, another way to measure that spread.
Okay, describing data is one thing, but how do researchers actually test their ideas, their hypotheses?
That's hypothesis testing. A common tool is the student t-test. It's generally used to compare the means of two groups.
Two groups, like what?
Well, a one-sample t-test compares your sample mean to a known population mean.
Yeah.
Like, does this drug significantly lower cholesterol compared to the average?
Okay.
An independent t-test compares two separate, unrelated groups, say, heart diameters in males versus females, and a paired t-test compares two measurements on the same subjects, like blood pressure before and after a treatment.
Makes sense. But what if you have, say, 3 or 4 groups? You can't just do a bunch of t-tests, right?
You could, but it increases your chance of making an error. So for 3 or more groups, you'd likely use an F-test, or more commonly, a ANOVA analysis of variance. Yeah, a one-way ANOVA basically extends the t-test logic. It lets you compare the means of 3 or more independent groups simultaneously, like analyzing river chloride levels across spring, summer, and fall.
Got it. And what if one data point just looks weird, way off from the others?
That's a potential outlier. There are statistical tests, like the Q-test or Dixon's Q-test, designed specifically to help decide if a suspicious value in a small data set should be legitimately thrown out or kept.
Interesting. Can we use data to predict things? Like future trends?
Yes, that's what regression analysis is for. It helps predict an outcome variable, y, based on one or more predictor variables, x. The goal is finding the line of best fit through the data points.
So you can estimate relationships and make predictions.
Exactly.
And finally, briefly, significant figures. They seem like small details, but they matter.
They really do. They indicate the precision, the reliability of a number. Using them correctly in calculations ensures your answer doesn't falsely claim more precision than your measurements actually support. There are specific rules for how to handle them: in addition, subtraction, multiplication.
It really shows the level of rigor involved. The next time you see a chart or a statistic, knowing all this, it gives you a real appreciation for the thought behind it.
Definitely. It's not just numbers thrown on a page.
We focused a lot on numbers, labs, measurements. But so much understanding comes from, well, people. From understanding human experience. That's where qualitative research really shines, isn't it?
It absolutely is. Qualitative research tries to understand a problem from the local population's perspective. It gives you those rich, complex textual descriptions of the human side of things.
Behaviors, beliefs,
Yeah.
emotions, the messy stuff.
Exactly. Often contradictory stuff. It's great for identifying those intangible factors,
Sure.
social norms, gender roles, ethnicity, things that numbers alone might miss.
And one thing that struck me from the sources, qualitative work often prioritizes deep understanding of a specific context over trying to generalize broadly. That feels different.
It is different. Its strength is depth, not necessarily breadth like some quantitative studies aim for. Common methods reflect that.
Like what?
Well, participant observation, where the researcher actually immerses themselves in the setting to observe natural behaviors, in-depth interviews, which are great for personal stories, sensitive topics.
Getting that individual perspective.
Right, and focus groups, which are really effective for exploring shared cultural norms or getting a broad overview of issues within a particular group.
And the key difference seems to be flexibility. Open-ended questions, letting people answer in their own words.
Yes, that flexibility is crucial. It allows researchers to probe, to follow unexpected leads. It leads to meaningful, culturally relevant, often surprising, and just plain rich information.
And sampling works a bit differently here, too.
It does. You might use purposive sampling, selecting participants based on specific criteria relevant to the question, often continuing until you reach theoretical saturation.
Meaning you're not really hearing anything new anymore.
Exactly. Or quota sampling, where you decide beforehand how many people with specific characteristics you need, maybe to mirror population proportions.
Like ensuring a balance of men and women.
For instance. And then there's snowball sampling. You ask participants to refer you to others they know who fit the criteria. Really useful for accessing hidden populations that are hard to find otherwise.
So once you know who you want to talk to, how do you actually get them involved? The recruitment part.
That's the recruitment strategy. It needs careful planning, but also flexibility. It often involves consulting community leaders, being really respectful, and always emphasizing that participation is voluntary. No pressure, no coercion.
And special care for minors, obviously.
Absolutely. They're considered a vulnerable population. You typically need parental consent and the minor's own assent or agreement.
Knowing these methods, it helps you appreciate the stories behind the headlines, doesn't it? The nuanced understanding qualitative research can bring beyond just the stats.
It provides that vital context, the why behind the what.
Okay, so whether we're measuring chemicals or listening to life stories, there's one thread running through everything: ethics. Our sources hammer this home. It's the absolute backbone.
It truly is. Research ethics is mainly about how researchers interact with the people they study. It's about considering participants' needs, ensuring proper oversight, building trust.
And the participants' well-being comes first. Always.
Always. The well-being of participants is the top priority. The research question itself is secondary. There's a powerful quote. If a choice must be made between doing harm to a participant and doing harm to the research, it is the research that is sacrificed.
Wow, that really sets the standard.
It does. This is grounded in the principles from the Belmont Report. First, respect for persons. That means respecting autonomy, letting people make their own decisions, and protecting those who might be vulnerable. Dignity is key.
Okay, what else?
Second, beneficence. That's about minimizing risks, and that includes psychological or social risks, not just physical ones, and maximizing potential benefits for the participants.
And third?
Justice. This is about fairness. Who bears the burdens of research? Who gets the benefits? Justice means distributing those risks and benefits fairly. Those who participate should ideally share in the knowledge gained.
And I remember seeing a possible fourth principle mentioned, respect for communities.
Yes, some ethicists propose that. Respecting the values and interests of the community as a whole, especially when the research involves community-level knowledge or relationships, protecting the community itself from harm.
A really important tool for respecting persons is informed consent. But it's more than just getting a signature, right?
Oh, much more. While written forms are common, especially if there are risks, informed consent is fundamentally a process. It's about making sure people truly understand what participation involves, the purpose, the time, risks, benefits, that it's voluntary, how confidentiality works so they can make a genuine informed choice.
And that process might involve talking to community leaders, holding meetings.
Exactly. Distributing info sheets, whatever it takes for clear understanding. For things like in-depth interviews or focus groups, you usually need individual consent, covering all those key points.
And consent can be oral sometimes, not just written.
Correct. Especially for minimal risk research. Or, interestingly, if signing a form would be the only thing linking the participant to the study, potentially creating a confidentiality risk itself. In those cases, oral consent might be better.
Speaking of confidentiality, that seems extra critical in qualitative work, given how personal it can be.
Absolutely vital. Researchers, data collectors, they have to maintain strict boundaries. Never share what one participant said with another. You need clear strategies for protecting confidentiality before you even start collecting data.
So training is important here.
Strongly recommended. Formal ethics training and certification for anyone interacting with participants or their data. It reinforces these crucial principles.
Understanding these ethical guidelines, it really empowers you as a consumer of information. You can ask tougher questions, not just what did they find, but how did they find it? Was it done responsibly? Ethical.
That's exactly the right question to ask.
Wow, what a journey through the whole world of research, from digging into what research even means to the ethical compass guiding it all. It's so clear that reliable knowledge is built on this foundation of, well, rigor and responsibility.
It really is. We've touched on how researchers frame problems, how they gather all sorts of data, primary, secondary.
How they evaluate it with statistics, understanding precision, accuracy, testing hypotheses.
Right. And how they delved into the human side with qualitative methods, while always prioritizing safety and ethics.
It's all about building credibility, finding genuine insights, and helping us all make better, more informed decisions, whether we're talking about river water or human societies.
It applies across the board.
So here's something to think about. The next time you encounter a new fact or a finding, try looking for that invisible blueprint behind it. Ask yourself, was the problem clearly defined? Were the methods sound, precise, reliable?
Was the analysis thorough? Did they consider different angles? And crucially, if people were involved.
Was that human element handled with the utmost respect, the utmost care? What new questions does thinking like this spark for your next deep dive into information?